All right, make sure you're connected to Woo Clap because we're going to have 5 or 6 questions on Woo Clap.
Yeah, give me a second. I need to. I've never connected on my phone, so.
Do you have a camera? You should be able to
A camera?
use this to connect.
No way.
Yeah, I'll just. No,
It worked with an iPhone by default.
in this modern day, I do not have a camera. Sorry.
Sarcasm.
Yes.
With I can't verify if it'll work with the default Android camera app, but it does work with the default by Apple one.
Tell me if I connected.
One person's connected. I don't know which one of you it is. Is this Decay's? Yeah.
Jessica.
Yeah, just go ahead and read it over one.
I mean, if you want me to do it.
Okay, well, I'm going to get started. So today we're talking about radioactivity. I'm going to lecture for an hour or so, maybe a little more, and then we're going to do an activity where we explore how radioactivity works.
Should I have to take my thing for notes?
You can always listen to it later or look at the pages online. Because if you don't have, then you don't have. So radioactivity results from radioactive decay. Now, when you think of radioactivity, what do you think of?
A radioactive.
Of what?
Chemicals.
Chemicals?
Chernobyl.
Radioactive.
Chernobyl.
Yeah.
Chernobyl is a good one. I remember that well. I was in college at the time.
I need a copy of the lab.
Or maybe it was high school. Okay. During our break, I'll go make a
Oh,
coffee.
thank you very much.
Well, after I lecture, we'll have a break before we start the. So, radioactivity is when you have something coming from the nucleus of an atom. So, chemistry, we're talking about the relationship between one atom and another. Radioactivity is talking about something that's occurring in the nucleus of an atom. And when something is radioactive, it's unstable. I'm going to use this because maybe it's less stable than the example I used yesterday. So if I can get this balanced, which, yes, it's too unstable, I can't really get it balanced. Okay, so I have to go to what I used yesterday.
It's so radioactive, you can't balance it.
Right. So here is a pen that's balanced on the end. It's somewhat stable. That is, it's staying balanced. But if I bump the table hard enough, and I'm just not going to try to bump the table like I did yesterday, but if I hit it a little bit, it'll fall over. Now it's in a more stable configuration. That's what's going on with radioactivity. You have the nucleus that was in a somewhat stable but not very stable configuration, and then it spontaneously falls to a lower energy state that's more stable. And when it falls to a lower energy state, just like the electrons in an atom, when they fall to a lower energy state, they give off light, such as what we saw with this in class yesterday. You have something that comes out of the nucleus. And that something could be a lot of things. We usually just talk about alpha, beta, and gamma, decay, but there's a lot of other things it can be. So that's what radioactivity is about. Most of the radiation that we encounter is just natural. Now, when I talk about radiation is a little different from radioactivity. Radiation means something is traveling out from something, right? It's radiating. And a lot of the radiation we encounter comes from the sun, because the sun has what we call a solar wind. It's blowing particles away from it. Those particles include protons, neutrons, electrons, and, of course, photons, the particle of light. All of those are radiation. These light bulbs are emitting radiation. The visible light is a type of radiation. So we have radiation all around us. And the radiation coming from the light bulbs is clearly non-dangerous to us. The radiation from the sun, a little more dangerous. Cosmic rays are pretty much just the same thing as the solar radiation, except for they're not coming from our sun, they're coming from outside of our solar system. So we have lots of radiation we naturally receive, but then there's also radioactive elements that will give off radiation. So if I were to have a very sensitive radiation detector, I could come to each one of you and I would be able to measure that each one of you is radioactive. Now, who thought that you were radioactive? We kind of, okay. Annabelle thought she was radioactive. Most of it, yeah, she knew already. Most of us presume no. Radioactivity is something that we don't generally encounter. But the food we eat is radioactive. Bananas have radioactive potassium in them. Most of the potassium is not radioactive, but a small percentage is. So radioactive materials are all around us, and we shouldn't really be scared of radioactive materials. What we should be scared of is too much exposure to them. So here's an example that we're going to come back to for the very end of the lecture, carbon-14. You guys have heard?
How many bananas would it take for it to be too many bananas?
Way more than you're ever going to see.
I love that. What if we look too bananas?
So
Sorry.
carbon-14, you've all heard of carbon-14 dating, right?
Yeah.
Carbon-14 dating relies on the fact that the solar radiation, in this case neutrons from the sun, strikes nitrogen atoms in the atmosphere, creating a carbon-14 atom. It changes them from nitrogen to carbon, actually. But that carbon-14 is radioactive. It's not stable. And so it will decay over some period of time into something else. Actually, back to nitrogen, I believe. So radiometric dating using carbon-14 is taking something that's in the air that we're breathing. So the air we're breathing in contains radioactive elements in it, like carbon-14.
Oh my God.
Carbon-14 dating wouldn't work unless what we breathe in was radioactive. So it's all around us. But if you have too much, well, then it can be dangerous. So, first woo clap question. And remember, www.wooclap. So when an atom undergoes radioactive decay, it...
Oh. What is it? Is it SCN something?
SCNC. 111. Now this is a question that I have not lectured on. This is what you think is going to happen to the atom when it undergoes radioactive decay. All four connected, but only one answer so far.
Yeah, mine is definitely making me register.
Register?
Yeah.
You must have texted me.
I don't know, man.
Here. It's me.
Help.
A little help from your friends.
What's an isotope again?
Okay, what's an isotope?
Thank you.
An isotope is an atom that has the same number of protons, but a different number of neutrons. Okay, we have three answers.
Oh, what? I'm sorry.
Okay,
Yeah.
so we had 2, 1, 1, 0. Now, this is a case where I asked the question beforehand, so I don't feel bad at all about the answer distribution. This is what you thought radioactivity resulted in for the atom. Now let's go back to where is radioactive decay occurring?
I have a question.
Yeah.
Are we doing a lecture all day today?
No, we're doing a lecture. I guess you weren't here to be in class.
Yeah.
I'm going to lecture for around an hour, maybe a little more, and then we'll do the lab.
An hour? You're going to lecture for an hour?
Yeah.
Oh, I should have brought my notes.
Why?
Oh.
So we make sure
I know,
that
I
you
should probably
understand what we're doing in lab.
I didn't know that. Lecture.
So where is the radioactive decay occurring? In what part of the atom?
In the atom.
It's in the nucleus. So it's a change in the nucleus. Now, the nucleus can do a couple different things. If it gives off what we call a beta decay, the nucleus remains unchanged. It's like my example with the pin. It's in a lower energy state, but it's still the same pin. Nothing has changed. I did an example. I'll do an example here. I'll take some of these dice, and I think we would all agree this is not the most stable configuration for the dice, but it's a way of illustrating a radioactive nucleus. So here I have a nucleus with protons and neutrons in a very unstable configuration. And so if it gets disturbed by something, it falls down. Here we had, the whole thing didn't fall down, unfortunately. The whole thing falls down. We have all of these clumped together, but we have these two things that are away from it. They left. So what I'm left with for the nucleus is less than what I had. I have these pieces that left. So sometimes you'll have something that actually leaves the nucleus, so the nucleus is changed. So the correct answer is it may or may not turn into a different element. Because if the nucleus changes, if you lose or gain a proton, then it's a different element. If you lose or gain a neutron, it's a different isotope. If you don't lose or gain anything, then it's just the same and unchanged. So the correct answer here was, no, don't feel bad. I hadn't lectured on it before. This was your preconceived notion.
We all got it right. We just didn't expand enough.
It was your preconceived versus after you've learned.
Aren't all the answers right then? Or not B?
Well, completely different element is possible. Isotope is possible. A
is wrong.
Well, A is wrong because it says same element. If it changes to a different element, it will be an ion. But if it's the same element, it won't. So A was wrong. So, in studying radioactivity, scientists like Marie Curie discovered that there were 3 very common types of radiation that they could differentiate by just using a magnet. One type of radiation in the magnet would, move out of the way. One type of radiation would curve a lot when you put it in a magnetic field. One would curve the other direction a little, and one wasn't affected at all. Now, you haven't learned about the magnetic force, but magnetic force,
Is that a Y? Gamma's Y?
That's gamma.
Gamma's Y.
No, gamma's gamma. That's how you write a gamma.
But it looks like a Y.
But Y is actually doesn't look like it. In Greek is a Y, but it's not gamma. It's, I can't remember how to say it. Yeah, a capital gamma looks like this, which isn't anything like a Y. So it's a lowercase gamma, not the uppercase.
Oh, it's like a hangman.
That's what capital gamma looks like, yes. And of course, it's G. So they broke this down to 3 types, and then they named them based on their penetrating power. Penetrating power is how easy is it to stop this radiation. So the first one, alpha radiation, is very easy to stop. Alpha radiation, if I take a piece of paper and I hold it between me and the radioactive water, it'll completely stop it.
Water's radioactive.
Yeah, it blew up the world enough that everything's just now radioactive.
The amount of, it's radioactive, very, very tiny amount. So alpha particles,
Sorry.
why are they called alpha particles?
Because they're alpha.
Not
They're
big,
weak as
they're
well.
the easiest ones to stop.
Which is weird.
Because alpha is usually the strongest, but
It turns out that the alpha particles are the biggest. They're the most massive. An alpha particle, as you can see in this picture, is 2 protons and 2 neutrons, which is a helium nucleus. We put a plus plus to say that it's missing the 2 electrons. So an alpha particle is the biggest, and that's why it's the easiest to stop. Now, the beta particle is just an electron. An easy question to answer, or to ask, not an easy one to answer, is how do you have an electron come out of the nucleus? Remember, radioactive decays are things that are occurring inside the nucleus. But what things are inside the nucleus? What things do we call nucleons?
Protons. Really?
Protons and neutrons.
Oh darn it! I got one.
We're
a
did it
team.
together.
Can we do our test together?
Okay.
We did.
Okay, now I didn't promise that. Okay, so protons and neutrons, those are the things that are in the nucleus. So how do you get an electron out of the nucleus if it contains no electrons?
Yeah, you think it out the energy level.
I have no idea.
No, because those are not in the nucleus. There's electrons orbiting the nucleus. And so the answer is actually really complicated. They're actually created. But what happens is you have a neutron, we'll use N for a neutron, that decays, making a proton and an electron, and one more thing that we actually call an anti-electron neutrino. Don't worry about this equation. What's important here is that the beta particle is an electron, and it is created when the neutron decays.
Yes.
Crazy.
So it didn't exist in the nucleus, but it was ejected from the nucleus because it was created during the decay. Then we have the gamma particle, and the gamma particle is light. Now, it's not visible light. It's in a much higher frequency than visible light, but it's the same type of thing as light. It's a wave.
Don't we want to gamma rays?
We are giving off actually infrared rays.
Oh, okay.
So we're giving off electromagnetic radiation, but it's in a much lower frequency, which means a much lower energy. These are very high energy waves. So you need to know those three types of radiation, what they are, why it's alpha, beta, gamma. Alpha is the easiest to stop. Beta, if I hold up like a little sheet of lead, it'll stop all the beta. Gamma, I'm going to need some thick protection to protect me from the gamma radiation. So when you go to the dentist and they take an x-ray of your jaw,
That's why they run to Texas.
they put a big heavy lead vest over you to block what is effectively the same thing as gamma radiation. X-rays and gamma radiation are fundamentally the same. The difference is where they came from. X-rays don't come from the nucleus of an atom. Gamma rays come from the nucleus of an atom. Okay, so here is a breakdown of information about the alpha particle. We've already seen pretty much all of these things, except for here, it'll cause significant damage to the surface of a material. So for instance, alpha particles, you can stop them with, a piece of paper, but if those alpha particles hit your skin, they'll cause damage to the skin because that energy is going to be absorbed and it will then break bonds in your cells. So you don't want to be exposed to it. But if you do, your skin's going to protect you. Unless you eat something that is an alpha emitter. If you eat something that's radioactive, that's going to give off alphas, then you know it's going to be absorbed inside your body, and that's more dangerous. So one of the very fundamental rules about radioactivity is if you're working with something that's highly radioactive, you never have something that you're going to consume around. So you don't want to have bubble gum or water or anything else when you're working with radioactive materials, because you get that gamma or the alpha emitters in your body, then that's going to be dangerous. Now, have you guys heard about radon gas and the dangers of radon gas?
Yes, my dad talks about it all the time, like it's a conspiracy theory.
Conspiracy theory?
Like,
Tell me more.
He just talks about it and I zone out because I get annoyed.
No. Okay.
Sorry, I can't tell you much more.
Oh, I'm assuming radon's actually not that dangerous then.
Probably
Well,
not.
yes and no. So radon is a gas, and it is one of the products of the decay of uranium. We have naturally occurring uranium in the earth. And as that uranium decays, it produces thorium and radium. Make sure I follow this right. And then radon and then polonium. Radon is the only gas in that sequence. Everything else is a solid. Well, what does that mean? That means when the radon atom is produced, it can go flying away from the rock. All the other things are stuck in the rock, but the radon can move out. And so then the radon can float around in the air, and it can attach to like a dust particle. You breathe it in, and the radon actually has a pretty short half-life, but you have its next product, polonium. If the polonium is on a dust particle then that you breathe in, and the polonium decays in your lungs, it'll damage your lungs.
How badly?
How badly? Anytime you have that. Yeah, it's all random as far as statistics.
Oh.
But every time you have one of those decay, the energy is going to be absorbed by something. That energy absorption is likely to break a bond.
I'm getting a headache. I need my glasses.
I feel
Notes as well.
in your notebook.
That energy absorption is likely to break a bond. And when you break a bond, you break a chemical bond, the most likely thing to occur is it just repairs itself with no damage whatsoever. So the most likely thing is no damage. But there's a chance that the bond reforms incorrectly. And if it reforms incorrectly, the most likely thing is whatever you're dealing with dies. When something dies, well, that's bad, but it's not life-threatening generally. And then the third option is it can reform incorrectly and still live. Then we call it a mutation. And if that mutation reproduces, then we call it a cancer. And so there's a cancer risk there. Now, I talked about those options, cells dying. Have you ever heard of radiation sickness?
Oh, you told me about this in your office. You throw up like a day later.
That's right.
It's like when you get radiation, you can't.
When you get a lot of radiation, the most likely thing from radiation is nothing happens. But the second most likely thing is you're going to have cells that die. So if you're getting radiation treatment for cancer, that's what they're trying to do. They're trying to kill cells. They will also produce some mutations in that, but they're hoping they kill everything, even the things they mutate they want to kill.
Kill
Right?
it before it kills you, basically.
But if you get a whole body exposure that's high, you're going to have a lot of cells that die. And radiation sickness is the body's response to having too many cells dying. The body naturally will replace cells when they die, but if you have too many die, the body can't keep up. And then the whole body fails, and you die. So radiation sickness is the whole body failing because of too high a doses, too many cells dying all at once. Keeping on with alpha radiation, if you have this alpha particle, that's 2 protons and 2 neutrons, if it's traveling through the air, it will naturally pick up some electrons. And when it picks up electrons, how many electrons, if it has 2 protons, how many electrons does it want to pick up? 2, right, because it naturally wants to be neutral. And then it just is a hydrogen atom. So these alpha particles will end their lives as hydrogen atoms after they collect a couple of electrons. And of course, we saw the last thing there. Beta particles,
Can I just take a picture of the last one?
if you like. I will post them in the middle, though, like
I
I said.
know, but I'm just gonna.
Anything to appease the anxiety really fast.
Okay. So beta particles, they're ejected from a neutron because there's no beta particles in the nucleus like we talked about. They are just electrons,
I love you.
and they lose energy at a slower rate, so they travel farther and they're harder to stop. So they penetrate fairly deeply into the skin, so they're much more dangerous to us. And once you slow them down enough, they're just ordinary electrons. There's no difference in one electron and another.
So these ones. Oh my God!
Go-
You're
okay,
going
go
so
ahead.
fast.
I'm sorry.
No,
So,
I go so fast.
So beta is not as strong. I mean, it's stronger than alpha.
It's like your middle bro. You know, like the guy with medium.
Saying stronger isn't a good comparative. It's more penetrating than alpha. Its energy may be higher or lower, which is what I think of as strong, but it's not an apt word because it doesn't really apply. But it's more penetrating than alpha because it's less interacting.
Okay, well, we're still on the same page. Sorry, Dr. Webb, we're not trying to slow you down.
It's okay.
We're just slow.
We have till 5, so we'll make it.
We have till 4.
No, lab ends at 5.
What?
Yeah.
Oh.
It's 3. Yeah. Honestly, I'm here for it.
It's too.
That's what's up.
Right now.
Yay.
So can I move forward?
You know what? Go for it.
Okay. Don't want to be going too fast.
Wait, how many protons and neutrons does beta have?
A beta is an electron, one electron.
Oh, that's it?
Yeah.
Oh, okay, it's chilling. I love that.
Now the gamma is a photon. We had photons in class yesterday. The photon is a particle of light. Oh wait, no, we didn't have them in class yesterday. That was a different class.
No, I'm talking about my drawing. Of my circle.
No, that might be some conversation up there.
Well, good. Those people in Tanzania that are going to watch this later are going to hear about your perfection in drawing a circle.
Yes. Okay, so the gamma is a photon, a particle of light or electromagnetic radiation. Some people will get really bent, say you shouldn't call it light because it's not in the visible range. It's the same thing as light, but it's a much higher frequency. And the energy is much higher.
So this one's super strong.
This one here is very penetrating. It's very hard to stop because it doesn't interact with much.
So yes.
Well, once again, no, because the energy may be higher or lower, but it's harder to stop.
Okay. I'm following.
That's kind of like saying that a BB is stronger than a cannonball because it's,
That's true.
you know, it depends on what you're shooting and how fast. But
Oh, he's so cute.
okay, so gamma rays, they're the same thing fundamentally as X-rays, except for X-rays aren't radioactive. They're radiation, but they're not radioactive radiation. They're coming from the electrons around an atom, whereas the gamma rays are coming from the nucleus of the atom.
So how many protons, neutrons, electrons, thingies do these have?
None, because they're light. That is,
Doesn't exist. I love that.
Yeah.
Just like germs.
they're packets of energy.
No, you can't say that.
So because they have no protons and no electrons, they have no charge, and thus they're not affected by the magnets. They're the ones that went straight through the magnets. Okay. Am I good to go to the next slide?
Yeah, maybe. I don't know. I'm not even thinking of I listen to them and then I can take
No
them like,
protons
oh,
or
and-
electrons or neutrons.
A gamma ray is none of those. That's correct.
That's what I'm recording.
Okay.
Not in
I'm
the
probably gonna be.
Forces.
Once in a while.
What's a force?
A push or pull.
Anything that pushes or pulls.
A force is a push or pull an object.
And we've learned about the gravitational force. We've learned about the electric force. Those are two of the four forces. The other two forces are the strong and weak nuclear forces, which are the forces involved inside the nucleus. Now, you still have the other forces inside the nucleus. But the strong and weak nuclear forces are unique in that they're very short-range forces. The strong and weak nuclear forces basically are so distant.
So it's all of them? The strong.
Well, they're all there, but the strong and weak nuclear forces are the only ones that are significant in the nucleus for the most part. The electromagnetic one is a little significant. Excuse me. But they're.
Are you okay? Do we need to quit class and take you to the hospital?
Did I give you bronchitis?
No, you need to
No.
drink water.
Yeah, for real. Here's some.
He's gonna die.
I will not.
YouTube
So-
is gonna hear this.
The strong and weak nuclear forces are so short range that they effectively are only nearest neighbor forces. So we have the four of you all in a row. With the strong nuclear force, there'd be an attractive force pulling Alex to both Jessica and to Josie.
Hi guys.
Hi.
And I'm gonna try to.
But Alex would not be attracted at all to Annabelle. She's too far away.
You're
You're too far away. I can't
Too
get
far.
tracked into you.
For the strong nuclear force, because it's so distance dependent. So in this graphic, you see it's showing if you have two nucleons, protons or neutrons, this force works equally for protons or neutrons. It doesn't matter what the electric charge is because it's not an electric force, it's a different kind of force. If you have two nucleons that are right next to each other, the strong nuclear force is going to be extremely strong, holding them together. The electromagnetic force will be strong, but not nearly as strong. But if you separate them a little bit, the strong nuclear force goes to zero, insignificant. The electromagnetic force just weakens a little.
Just curious, gamma rays are light?
Yes. So what is the important thing I'm talking about with this slide?
Attraction.
The attraction between
Nuclear forces.
Okay, the strong nuclear force is a very short range force.
yeah, 'cause you said
That's the important thing here.
Yes.
So, woo clap question. The strong force is a force in the, where does it occur?
Why do you ask these questions before we know the answer?
No, this is right. I just finished talking about this.
Oh, okay.
Well, sometimes it's to get us to get a base knowledge or try to understand base knowledge before we actually have base knowledge.
Well,
But I feel stupid.
Yeah, me too. I think when teachers do it.
when you do the pretest, it's to check the
You're just trying to
understanding
gauge your
beforehand.
We're not on the gauge.
I'm like way below. Like if the gauge is here, I'm way down.
You just need enough for you to turn it down. So if we get it wrong, he knows. It's okay. It's helping us too. Yes, it is helpful. Sorry, my inner teacher is trying to help another teacher out. It just happens.
Okay, thank you, Jessica. We have 3 answers so far.
Yeah, I'm still working on my answer.
Okay.
Trust me, I just guess it's okay. But I don't want to judge you.
Okay,
Oh no.
Okay. we had one person that said it holds electrons in orbit, 2 that said it holds nucleons together, and 1 that said both. Okay, the point of the preceding slide was that it's very short range, only next neighbors.
Was that
The
right?
electron is too far away, and so it's not going to affect the electron.
I'm sorry, that
Also,
was me.
another thing to keep in mind,
Wrong.
the electron actually is not affected by this force, even if it was right next to it, because there is a certain type of charge. It's not electric charge, it's not magnetic charge.
I just thought that orbit meant that they were being pulled together. I'm sorry.
Well, the electron is being pulled in to orbit, but it's not the strong nuclear force. The strong
It's a
nuclear
different
force,
that's doing
yes.
that? Okay.
The strong nuclear force is only active between nucleons, so only between nucleons, and only through next neighbors. So it's only in the nucleus. So that then begs the question, what is holding the electrons in an atom if it's not the strong nuclear force? And the answer, it's the electric force.
So what's the answer?
The answer to this is B.
Can you go back to 2 seconds? The last slide.
I'm stupid.
Yep. Good, thanks.
You're not stupid.
Wait, what was it?
No, I'm just stupid.
P.
I got it right.
Good job. I'm proud of you.
I done guessed it.
Okay, so this graphic here is just reiterating, it's always attracted. Protons are attracted to protons, neutrons are attracted to neutrons, protons are attracted to neutrons. That's because it's not dependent on the electric charge. It's dependent on the color charge is what we call it, a different type of charge.
Wait. You're gonna need to repeat the last 2 sentences that you say because I'm trying to write them down, but I'm also trying to cover notes.
Me.
So protons are attracted to what?
Protons are attracted to other protons as well as neutrons.
Other
They're like by atoms, you know. I did a sexuality fun for you.
neutrons.
That,
I didn't get it.
Whatever you
Always
remember.
It is-
attracted.
it is a different type of charge.
So it's not electric
Protons are
charges.
attracted to protons, neutrons are attracted to neutrons.
And protons are attracted to neutrons. They're always attracted between nucleons. Doesn't matter which type they are. But you also have that electric force, the thing that's holding the electrons to the nucleus is trying to push the protons apart. In a hydrogen atom, you only have one proton. There is no bonding. But in a helium, you have two protons and two neutrons. The protons are attracted through the strong nuclear force, but repelled through the electric force. The neutrons are attracted by the strong nuclear force to everything in the nucleus, and there's no repulsion on the neutrons.
Wait, but so is this like the opposite of what we were learning before? We weren't learning that opposites attract.
That was the rule for electric charge, as well as for magnetism that we did study.
So this is the rule for the strong nuclear.
Yeah, which is more like gravitational force, where everything is attracted.
So what should I label it? Gravitation.
It's the strong nuclear force.
I'm sorry.
So the strong nuclear force is always attractive. But the electric or electromagnetic force between protons is repelling, and neutrons have no electric force. Because of this, if you start to get big atoms, you get more and more positive charge if you have a bigger atom. And those positive charges are trying to pull it apart. And the positive charges have a long range for their repulsion, because that slide a few back that showed the meters, the electric force is significant at long range. So as you get a nucleus like uranium that has 92 protons in it, you have to throw more neutrons in there to hold it together, because the protons would push it apart. The reason our large elements are radioactive is because they have so many protons, they're trying to push them apart. Which is what this slide is showing you. You have the neutrons to help space them apart to weaken the repulsive force and give you more attraction force. Half-Life. Anybody played the game Half-Life?
It sounds like something my dad would say, why are you playing that?
There's a game.
Yeah.
Yeah.
I've never played it. I don't know anything about it, but I'm just trying to look for any
Familiarity with the term. Half-life is a term that's very important when we talk about radioactivity.
Oh, is it like Halo?
I think so, yeah.
What is Halo?
I know of Halo.
It's a first-person shooter.
Oh, okay.
So,
It's same thing. Yep. Except that you're a physicist who battles aliens.
Sounds good.
Ew, I
Okay.
After Web, I
So-
figured out your next profession.
All right. So the half-life is the time it takes for a radioactive sample to decay, so you only have half of what you started with. Now, radioactive decays are a simple statistics thing. If I have a bunch of dice here, this is what you're going to do in lab, and I say, okay, what's the chance that I throw one die, the singular for dice is die, what are the chances that I throw one die and it comes up showing a 6? 1 out of 6. So on average, how many times would I have to roll the die before it comes up with a 6? But of course, it had 6 the first time, or the second, 2 the third, 3 the fourth, 4 the fifth, 2 the sixth, 1 the seventh. We didn't match that odd. 5 the 7th or 8th, I forgot what my number is. 8. 3 the 9th. But it's a random situation, but there's a certain probability of it coming up as 6. The same thing is going on with the nucleus. It's a random chance of the nucleus decaying, but there's a certain probability every second that it's going to decay. So the half-life is saying, based on that probability of decay each second, if it's more probable, it's going to take less time for it to decay to half. If it's less probable, it's going to take more time for it to decay to half. So the half-life is different for different radioactive elements because
they have a different probability of decaying each second. So the half-life, what is the half-life again?
When is time required for half the original quantity?
Okay, it's the time required for half the original quantity of the element to decay. So if I start with 100 kilograms of a radioactive substance and it has a half-life of 1 hour, how much mass of undecayed atoms do I have after an hour?
58.
Okay, and if I go another hour, how much do I have? 25, because it cuts it in half every hour. And so you can actually make a simple equation. The number of radioactive nuclei is equal to the number you started with divided by 2 raised to the time divided by the half-life. I put T 1/2 for the half-life. So if it's 1 half-life, it's going to be N0 divided by 1. If it's 2 half-lives, it'll be N0, or excuse me, not 1, divided by 2 to the 1. If it's 2 half-lives, it's N0 divided by 2 to the 2. If it's 10 half-lives, it's N0 divided by 2 to the 10th power. When would you run out of radioactive elements with that equation?
Technically never, because it's just going to keep getting smaller into multiple infinite decimals.
Very good.
Yay.
Yay! So, to make sure that we all pay attention to this dialogue, a certain isotope has a half-life of 1 day. This means that the amount of the isotope remaining at the end of 2 days will be
Thanks. A certain isotope
Remember, it's divided in half each time.
got this one right. If I didn't, I'm gonna be upset.
okay. We had one person that said 0, 3 that said 1/4. The 1/4 is right. Remember, 1/2 every half-life. So after 2 half-lives, it's not 1/2 plus 1/2. It's 1/2 times 1/2, or 1/4. Any questions?
Ah!
You got it right, by the way, Annabelle.
Thanks.
Wait, how do you know?
Because she put hers in third, and then she said, I got this. So,
Oh, okay.
that's how I knew. Yes, because there's nothing up here that tells me. So when you have a decay, if it's decaying by alpha or beta mechanism, the nucleus is changing. It's transmuting. That was the whole idea back with the alchemist days. People wanted to do something like take copper. Copper looks a lot like gold. And try to convert the copper into gold through some kind of process. Mix these chemicals together and make gold. Well, it never worked. But with radioactive decays, you do have transmuting. You do change from one type of element into another type of element. So you can actually transmute elements via radioactive decay. So here is how carbon-14 is created in the atmosphere. It's a transmutation. Now, this is a radioactive relationship, but it's not a decay initially. You have a neutron that came from the sun that hits a nitrogen atom. The air is 79% nitrogen molecules. So lots of nitrogen up there. A neutron hits it, and it's absorbed. There's an intermediate phase that is nitrogen 15. That means it has 15 things in the nucleus, 7 protons, 8 neutrons. But then that nucleus is unstable and it decays, kicking off a positive charge. But it's not a proton. Yeah. It's what we call an anti-beta or a beta plus. In that case, you had a proton that decayed and produced a neutron and that positive anti-electron. And so it transmuted, it changed it from a nitrogen 14 into a carbon 14. Actually, no, it is a proton. I was wrong. It is a proton that leaves. It's not an anti-beta. I should think more carefully. So you transmuted nitrogen into carbon, made a new carbon atom that didn't exist before. Another example is the decay of uranium. Here we have uranium-238. That 238, that superscript number that's shown, is capital A. Do you remember what capital A stood for?
Oh, it's not back there.
And it's not back there.
Accelerate.
From class yesterday.
Oh, nope.
Oh yeah, the number of nuclei.
Or atoms, atomic.
It's the atomic mass number. It's how many total things you have in the nucleus, how many nucleons. And so uranium-238 has 238 protons plus neutrons. And I put P plus N, or I could have used the number that tells us how many protons, capital Z. Z is the atomic number that tells us how many protons. Capital N is the neutron number that tells us how many neutrons. This number down here is the number of protons. It's the atomic number. So you can determine the neutron number. We went through this in class yesterday just by saying, well, since the atomic mass is Z plus N, then N must be A minus Z. And so I can take this and say, okay, 238 minus 92 gives me 146 neutrons, which I shouldn't have wasted my time doing the math because it was written right there. So you know it has 146 neutrons because you can take the difference in the superscript and the subscript, and that tells you how many neutrons are in the nucleus. This is unstable. It decays into a thorium by giving off something that has...
Why does it say 2 plus 20?
It's not 20.
It says 20 though.
I know. I was just going to point that out. That 0 means 2 neutrons, 2 things with 0 charge. But it sure as life looks like a 20. When I was looking at my slides before class, I was wondering about that too. And wait. So this here, 2 protons and 2 neutrons. What do we call the radioactive product with 2 protons and 2 neutrons? It's an alpha particle. So this is an alpha decay because it spontaneously produced that alpha particle. You don't want to hang out too much with uranium, even though it's a naturally occurring rock. A lot of your rocks that you find, like granitic rocks, are going to have uranium in them. But it's not a very safe thing to hang out with because of that.
So what about when people work with uranium? Like my grandpa's wife's sister used to be a chemical engineer and like worked with uranium in Russia for a while. Like what? She's just wacky, and I don't know if it's because she's been hanging around that stuff too much, or that's just her.
It of course depends on how much you're around it and what kind of protection you use. Remember, alpha particles you can stop with like a piece of paper. So as long as you're wearing, wear something like protective clothing, like they have these days, you wear like a paper suit, and then make sure you're covering your face, and you're good. Because it's an alpha emitter, right? If it was a beta or gamma emitter, you would not be good.
Did they know this in the 80s?
In the 80s, yes. In the 40s, no.
No.
And so there were a lot of people who did things like making glow-in-the-dark dials for the military. They used a radioactive paint. And you'd have these, mostly ladies were hired to do this, and they'd be painting it, use their tongue to wet the thing. And then they end up with a tongue cancer because they put all the radioactive stuff in their tongue. us. Other types of radiation now, the beta. Beta results in no change in the mass number because what it did was convert a neutron to a proton. But in converting that neutron to the proton, the atomic number increases by 1. Z, remember, is the atomic number, the number of protons in the nucleus. So if I were to have a gold atom have a beta decay, now I'm just making something up, I'm not saying gold has beta decays. It would go from having 79 protons to 80 protons, and it would become a mercury atom. And I feel really sad because mercury is not nearly as valuable as gold.
We're safe.
So that's what a beta decay does. It transmutes it, it changes it to a new element. Gamma radiation, notice it just has no change. No change in mass, no change in atomic number. You can't tell the difference in the atom before and after, except for if you do very precise mass measurements, because the mass changes. The photon carried away energy, and Einstein said E equals mc squared, so if the energy changes, the mass changes. Artificial transmutation here is bombarding a nitrogen atom with an alpha particle and causing it to change into an oxygen. So we can manually force atoms to change from one element to another by bombardment. And that's how we have those elements above uranium, that neptunium, plutonium, americium, curium, berkelium, californium, etc. Those were created by bombarding a nucleus with particles like neutrons and protons and alphas to see if they can make them absorb something and become a bigger nucleus and change it into a new element. So, not our last. When an element ejects a beta particle, what happens to the atomic number? Okay. According to this slide, what would the answer be? It increases by
I was
1.
in the middle of writing that and you switched, so I didn't.
So when you have that beta decay, you eject an electron from the nucleus. And so when you eject that electron from the nucleus, it had to come from somewhere. And what happened was a neutron decayed into a proton and that electron. And so the number of protons went up by 1 in that decay. So the correct answer was it increases by 1.
So none of us got it correct.
That is correct. Radiometric dating. Radiometric dating, you're taking something and you're saying how much decay has occurred, and based on how much decay has occurred, you figure out the time. So just taking a random example, carbon-14 has a half-life of 5,630 years. Actually, it's 5,760 is what it says here. It's 5,730. I said it wrong, so we're both wrong. 5,730 is the actual number. Let's say you started with 1,000 kilograms of carbon-14. How do you know? I don't know how you know. I'll write it that way. 1,000 kilograms of carbon-14. And sometime later, you come by and you measure and you say, wow, now there's only 25 kilograms of carbon-14. How long have you waited?
4 years.
Okay, I will make it so it's 4 years.
What?
No, I can't make it so it's 4 years. How long have you waited? I actually meant to put 250.
Years.
I actually meant to put 250 there because that's a math you can do in your head. How much do you have remaining?
If you start with 1,000, you have 250 remaining. What fraction is remaining? What fraction?
Let's get it back.
1/4.
That's 1/4. So if you have 1/4 remaining, how many times has that mass been cut in half?
4, 3, 2.
Twice.
It's 2.
1/2 times 1/2 is 1/4. So that means it's gone through 2 half-lives. So it would be 2 times 5,760 years old, if that was the right number. So it would be, 11,520 years old. That's how radiometric dating works. But there's, of course, some inherent flaws. Because how do we know how much of the atom it started with? You weren't there, so you don't necessarily know. So you have to make some assumptions. Now, the first bold and known wrong assumption is that, well, what's the fraction of carbon-14 to carbon-12 in the air right now? We can measure that, we can calculate it, based on that. If we assume that the ratio has always been the same, then we measure how much carbon-12 there is and how much carbon-14 is. We say, the ratio has dropped by a factor of 4, so it's gone through 2 half-lives. But once again, who's to say that that ratio hasn't changed? In fact, we know it does change. It'll change significantly. If you have a volcano erupt, that will significantly change the ratio of carbon-14 to carbon-12 in the atmosphere. So scientists have to do something else. They can't rely on that assumption that it was constant. A lot of creationists will say, they're assuming that it was a constant ratio. No, they're not. Scientists know that's not right. So what they do is they calibrate. They take things that you can get a known age for, things like artifacts that have been dug up in an archaeological dig, and by historical documents, this city was destroyed in this year. And then they do the radiometric measurements, knowing the time, they can then calculate what the ratio of carbon-14 to carbon-12 was when that thing died, because that's what you actually measured. So even though they weren't there, they can calculate what the condition was. Carbon-14 dating, from a creationist standpoint,
Garbage.
it's highly relevant. Because most creationists believe that the Earth, most young Earth creationists believe the Earth is around 6,000 years old. If the Earth is 6,000 years old, then something with a half-life of 5,760 years, that's really relevant. Because it's going to be basically within 1 half-life. But if you believe in either an old Earth creationist or the evolutionary idea, where the Earth is billions of years old, and life in this Earth has been around for at least 541 million years, then 5,760 years is a small amount. And if you go to 10 half-lives, you have less than 0.1% remaining. And carbon-14 just doesn't go that far. Carbon-14 dating can only go out to about 50,000 years because you just have too little carbon-14 remaining after that time. So carbon-14 to an evolutionary viewpoint is irrelevant. So what is relevant for people who believe in an old Earth? Using other radiometric decay sequences besides carbon-14. So I have some of them there. The uranium-238 decays. 4.47 billion years is its half-life. That's something that would be good for measuring the entire age of the Earth. Uranium-235, 710 million years. Rubidium-87, 48.5 billion years, or 0.8 billion years. And then potassium-argon, 1.25 billion years. Those are ones that are used regularly to date rocks by people who are trying to study the age of the Earth and the age of layers in the Earth. Nuclear fission. What do you know about nuclear fission?
It's pretty dang expensive.
Expensive?
Yeah, totally.
Somebody mentioned Chernobyl. This is what was going on in Chernobyl.
Oh, yeah.
I hope that's spelled right.
It's not, but I don't know how it's spelled right.
SCERNOBYL.
No, it starts with C.
No, yeah, you're still
You
right.
spelled it right if that's a Y at the end.
Yeah.
Isn't that a
Right.
horror
Well, it's a city. It's a city that they had a nuclear fission power plant that went kablooey. Bombs. Has anyone been to Hiroshima or Nagasaki?
Yes, I can afford to go there.
movie?
I take that as sarcasm. Well, Hiroshima and Nagasaki were destroyed by nuclear fission bombs. So that was all nuclear fission. What do all of these have in common? A lot of energy released. A lot of people got hurt. Nuclear fission releases a lot of energy, and it occurs by breaking a nucleus into smaller pieces, not just a little chunk like an alpha particle decay, but huge separation. So here's a typical nuclear fission reaction. You have the uranium-235, and you hit it with a slow-moving neutron. That slow-moving neutron is absorbed, makes an excited state uranium-236 that instantly breaks apart into two big atoms. This example shows krypton and barium, but it could form all kinds of pairs. And then it gave off some extra neutrons. The key to this is a lot of energy was released, and it took one neutron to start it, and you have 3 neutrons at the end. So this is kind of like, think about the coronavirus. If one person catches the coronavirus, on average, they're going to give it to 2 or 3 people.
Corn road
And so, what?
Corn road virus. Get it?
So because the number of people that it's transmitted to is bigger than the number that it came from, the size of the coronavirus will blow up. Based on the rate at which coronavirus infections are occurring outside of China right now, if it were to continue unchecked at that rate, before the end of September, we would have all contracted coronavirus. Because it grows exponentially because you have multiple reactions that can be caused after due to the first reaction.
Is it as bad as they say it is?
That's something I'm not really qualified to answer. I know one of my relatives who's a nurse was saying the standard influenza virus is actually a much bigger concern for our safety than the coronavirus.
I want to be honest with y'all. I want the Black Plague to come back.
I
I think that'd be like
every 100 years on the 20th year,
You
then
want to talk
disease
about
happens.
I just think it'd be very interesting because we have the technology now to tone it down compared to what they had back then. So we were be like moving our dead people around. Like,
Thank you, Typhoid Mary.
wouldn't
Getting
it?
back to
Y'all are just yes.
I'm never pro-death by any means. So, nuclear fission releases a lot of energy. That's all it's saying here. It's nothing different than what we had in the preceding slide. Because you have more than one neutron that comes off of each reaction, the rate of the reaction increases exponentially. That's the key, is the chain reaction exponentially increasing.
No teachers get paid enough to deal with it.
Now, I'm going to actually skip over this. I'm not going to ask you to know about nuclear bombs and critical mass.
Whoa, what the heck is that?
Uranium-235, uranium-238, and uranium-239 are different whats? Well, they're all uranium, so they're all element 92.
I don't like how they're spiked.
This
feels like they're not.
Uranium 235, plutonium 238. Ooh. I'm gonna guess.
You guessed right.
I did.
What's the answer?
Well, somebody else came in about the same time, so you might have been wrong.
What's the answer?
Okay, 2 people are right, 2 people are wrong.
Okay.
This here, remember I did the example of uranium 238 before, and this number up here was the atomic mass number, the number of protons plus neutrons. I put neutrons and protons. This here is the atomic number, the number of protons. And so if you have uranium is always 92. If it has 92 protons, it's uranium. Always the rule. So these are all the same elements, so everyone correctly ruled out element.
No, who is locked in a closet?
What was that?
Who are you holding captive?
That's the towel dispenser.
That's the what?
Towel dispenser. You know, like in the bathroom, you push the little thing in it.
Oh, it is.
Like paper towel.
It recognizes the sound now.
So isotones. Isotones and isotopes differ by the letter N and P.
Correct.
Isotopes have same number of protons.
Does acetone have the same number of neutrons?
Yep.
Oh my gosh.
So in this case, we have 92 protons in each case, but we have a different number of neutrons because the protons plus neutrons is changing. So they're isotopes.
Heck yeah.
Ion is a word we had from class. I don't remember if it was yesterday or if it was on
You're
Monday.
right? Oh, wait, the circle answer is the right one.
That's the right answer, yeah.
We were wrong. Jesus.
What are ions?
They're like, aren't they groups of atoms?
Actually, I'm pretty sure this is Monday's lecture. Ions are atoms that have a different number of electrons than they have protons. So there's nothing here to indicate if these have the same number or not of electrons. So they're not ions because you don't have the information to say that. And nucleons, well, they're not nucleons, they're nuclei. You guys seen this equation E equals mc squared?
Yeah.
What does it mean?
Energy equals mass times something. Velocity.
Okay, this is the rest energy equals mass times the speed of light. You can say velocity squared. The rest energy, the energy something has just because of its mass. I have more mass than all of you. That means I have more energy than all of you. Now, this isn't energy that I can use generally, although fat is the way we store energy. But we're storing energy in fat as chemical energy. This is energy just because it has mass. According to Einstein, mass is simply a form of storing energy. And that's the equation to tell us how much energy is stored in mass. So that equation is important in nuclear physics because if you are releasing energy, then that means you must be having a drop in mass because you had to convert mass into a different type of energy that you released. So that equation is used all the time in nuclear physics. So the energy that is released is equal to the mass difference times the speed of light squared. Now I'm going to show you a really cool graph. Well, this isn't the cool graph. This is a graph that shows atomic number versus nuclear mass, showing that you have more neutrons as you get to higher atomic numbers. That, for our purposes here, just isn't important. What is important is this graph. The mass per nucleon, mass per proton or neutron in the nucleus, as a function of how many protons you have. Hydrogen is the smallest nucleus you can have. And notice the mass of hydrogen. The mass of hydrogen has the highest mass per nucleon of any element. Why? Because it doesn't have any binding energy. It's not being held to another thing in the nucleus. Everything else, you have two nucleons or more being held together. What's the most stable nucleus? Iron. Iron is the most stable nucleus. You have the lowest mass per nucleon. It's kind of weird to think that a proton has a different mass in hydrogen compared to iron.
Wait, what's the scientific thing for iron? Like, where is it on?
Fe. It's Fe. It's what, 58, I think?
26.
No, 26. Okay. 26 and then 58 for the superscript for the number of protons plus neutrons. Yeah. So iron is the most stable nucleus, which means you have the lightest mass, the lowest mass for protons and neutrons in iron. So let's answer this question. In which of these nuclei does the proton have the greatest mass? You too.
We could. Let's do it right now. We can do a social experiment. I don't know who can sleep the longest.
You guys are cute.
Like, come at me, guys.
You guys need to talk to Amy. You'll find out that you would lose.
And technically, if we all guess, one of us would get it right.
Yeah, we're not that organized.
Looking at this graph, which element had the highest mass per nucleon?
Hydrogen.
Hydrogen.
What the heck? Sorry.
So the correct answer was hydrogen.
Did anyone?
No.
Dang. You see what I mean? We're not that organized.
Nuclear fission occurs by breaking something up here and moving toward here. Why? Because you're going toward the more stable nucleus, releasing energy in the process. So you're converting mass that you had in a uranium atom into energy and then these smaller particles in the process. But you could go the other way. You could start here and go this way too. There's a lot more energy available going from here to here, right? That's a much bigger difference than going from here to here. So historically, you guys know that the U.S. developed the atomic bomb. That was a fission bomb. We dropped two different variations on Japan. There was one dropped on Hiroshima.
Why are we hurting the Japanese people so much?
During World War II,
It was
they
World War
attacked us
II.
first.
Oh, World War II. I thought we were talking about like humans just cause.
Freaking Tuesday.
That's a Tuesday, let's bomb the Japanese. Like, no, that's not how it works.
No more.
No bomb. So the first bomb was a uranium bomb. The second bomb was a plutonium bomb. So some conspiracy theorists say, well, they want to drop both so they can compare them in real life to see how they compared in effectiveness. I don't really buy into that, but they were different. After the war, scientists realized, wait a minute, there's a much bigger potential for fusion.
Oh boy.
And so the government said, let's build a fusion bomb. Now, J. Robert Oppenheimer, the person who had led the Manhattan Project to develop that the nuclear bombs that they dropped at Hiroshima and Nagasaki, he refused. He said, no, we created something evil. I'm not going to be part of doing something to make something more evil.
I thought that they didn't know. They just got all of the scientists together and put them in different rooms, and they were each working on something, and they put it all together, and then they realized what they were making, and they were like, we're not okay with this.
America did that?
That could be true. I don't know
We did
if it
that?
is or not.
I don't
It
know.
certainly seems plausible.
Because it would seem plausible at the time.
The scientists who worked on it
by and large, they all felt very bad about what they've done. They use science for a bad thing. Science responsibility in science is important. It's not just, oh, we found knowledge, yay. What you do with that knowledge is important. And so there were some scientists who were willing to work on the fusion bomb. And it only took about 5 years, 10 years. And they came up with the fusion bomb, what you probably know of as a hydrogen bomb. Hydrogen bomb because hydrogen is the fuel that they're using for the fusion. And you can see that there's a much bigger yield for the hydrogen bomb than the fusion bomb for the same mass of fuel because of the vast difference in these energies.
How long is this lab gonna take?
20 minutes?
20 minutes? So, thank you, 20 minutes.
So the fusion reaction has a lot more potential for explosion, for energy. But like I said, we have to be responsible. Fusion can also be used for good. We have nuclear fission power plants. They're generally very, very safe. The problem with nuclear fission power plants is what do you do with the radioactive waste? You've dug radioactive material out of the ground. What do you do with it after you're done?
You bury it.
You bury it. That's the thing that makes logical sense. But we're concerned. If I bury it and somebody digs it up, I'm responsible.
Or if it seeps into the soil.
Or if it seeps into the water.
Or if someone
water
hits
gets.
it and it goes completely.
So that's what hampers our use of nuclear fission power plants.
Launch it into space and see what happens.
But what if it blows up and launched?
Well,
Hey, look, we just gave ourselves some nice nuclear fallout. Nuclear fusion doesn't have that problem. Nuclear fusion, typically you're fusing hydrogen into helium. Well, you can fill up some balloons and have some fun. There's really no downside to the waste product from fusion like there is from fission.
you need to stop making like nuclear stuff.
Well, I'm all for nuclear energy, for fusion energy. The problem is we haven't figured it out yet.
Yeah.
It releases so much energy, we can't control it. We can make a bomb because you don't control the bomb. But we can't really control it for a fusion power plant. The sun is a nuclear fusion device. Oakley used to have a slogan, thermonuclear protection, because the sun is a thermonuclear device. It's fusing hydrogen to helium.
But it uses gravity control, and we don't have something like that we can apply on Earth because we don't have enough mass. Okay, let us get started with the lab. So first we're going to take a break. Let's come back at 3:30 and we will start with the lab.
A break?
Yes. A break because you've been sitting here